Now, I'm sure by now you're getting really bored with these collections, which are just repetitions of collections you've already seen, but somehow I'm claiming that they are thread safe. So let's take a look at something which is different. I'm sure that many of you are expecting a concurrent list. Well, guess what? You're not going to get one. There is no concurrent list in the TPL. There is something else though. Essentially, let's just recap what we have so far. So we have the stack, which is a last in, first out structure. Then we have the queue, which is a first in, first out structure. But we also have a data structure called a concurrent bag. And the key thing about this structure is it provides no ordering whatsoever. It provides no ordering guarantees. Basically, you're going to add elements into this data structure, but the order in which they come out is unknown and can be virtually anything. So let's take a look at how that works. I'll do a more complicated example this time, something involving separate threads. So let's have a bag, and this is going to be a concurrent bag of int. So I'm going to make a couple of tasks. So let's have tasks equals new list of tasks. So I'll have, let's say, 10 such tasks. So for each of those, I'm going to do task.add and just make a new task using task.factory.startNew just so that we can start them at the same time. So for each of the tasks, I'm going to add this value I to the concurrent bag. So that would be bag.add I. By the way, this is something which is tricky in .NET, unlike C++ and other languages. So I'll introduce a local variable here, I1, for actually adding the element. So what we can do now is we can first of all indicate that the item has in fact been added by a particular task. So I'll do a write line here. We're going to say that task.currentID has added I1. So we've added the element, and let's try getting the element. So int result, and then if back.try peek. So peek is the thing that we're going to use to actually look into our concurrent bag out result, then we can print it out as well. So console.writeLine task.currentID has peeked the value and then result. There we go. So we're going to wait on all of these tasks. So I'll do a task.waitAll on tasks.toArray, like so. And well, we can start with this. So let's actually execute this and see what we get. So the index here on the left is the ID of the task, and the thing on the right is the value that this has actually added. One curious thing you can see is that the task, for example, task 1 added the value 0, and when that task went and looked at the actual value by using peek, it gets exactly the same value that is added. And if you look at all of these, you'll see that generally this is the case everywhere. So 10 has added 9 and 10 has peaked 9, or here 7 has added 6 and down below 7 has peaked the value of 6. So they're out of order, but they seem to be peaking the value that they've added, and this betrays the internal organization of Concurrent Bag. So essentially Concurrent Bag, what it does is interesting. It kind of keeps a list of elements per thread. So each of the threads has its own little bag of elements, and whenever you look into it, by default, because it's an unordered collection, it can give you virtually anything right. It has the right to give you virtually any element if you try to peek. So it just gives you the element from its thread local storage. Now, when you try to remove elements, that's where the fun begins, but it only begins if the thread local element has no element to give you. So for example, if you were to try and take out the element and the element associated with this thread had nothing in it, it would go to its neighbor, and that would be a more costly operation. But as it stands, the setup has been streamlined for efficiency. So you basically have lots of thread local storage there, and that's what's being returned here. And if we want to take an element out of the bag, once again, you have no idea which element will be taken out. There is no ordering. There is no idea of order inside the collection. They just get added randomly. But if you do want to take an element, you can just say int last, and then if bag try take. So you use try take to try get the element. Of course, this will fail if there are no elements in the back, but if there is an element, we can write out that I got last, and whatever we get here, so we get a 3, we can try it again, and we get a 0, we can try it again, and we get a 1 here, so you cannot really predict what that element is going to be. But this is a collection which is optimized for speed. So long as you don't care about the order of the values, so long as you don't care that they preserve the order they were actually added in, you can get a very fast bag of elements, and that's why it's called a concurrent bag. Let's talk about the producer-consumer pattern. It's actually a very simple pattern. The idea is that now that we've got these concurrent collections, what you can do is you can have a collection and you keep adding items from one thread, or indeed many threads, and you keep consuming the items or taking out the items and processing them from a different thread. And it all sounds great in theory, but in actual fact, we cannot do this just yet. The 3 types that we've looked at previously, concurrent bag, concurrent stack, and concurrent queue, they all happen to have the same interface implemented. So if I make a concurrent bag, and if you look at the hierarchy here, you can see that one of the interfaces is called iProducer-Consumer Collection, which you can actually go into it and take a look at what's going on here. So essentially this interface provides a few elements which are common to the concurrent queue, the concurrent stack, and the concurrent bag. And in fact, you can see that there is a triad, try-take, there is a to-array as well. You can see that instead of just an ordinary add, there is a triad. This is a bit bizarre because in all of those cases, adding an element should not result in failure, but this has been done to, basically it's been done just in case somebody creates a collection which has to be able to fail during an addition. But what the takeaway here, the main point I'm trying to make, is that they all implement an interface which is called iProducer-Consumer Collection. So essentially you might want to actually start using something like a concurrent bag as a way of collecting, let's say, the messages coming in from the network, putting them in this element, and then having a separate thread get these messages one by one and processing them. However, there is a bit of a problem in this approach, and the problem is that sometimes if you just leave a collection like this lying around, it will just overflow with lots of items being posted on from other threads, and maybe you want to somehow control what's happening. Maybe you want to say, why don't we have a collection which can only store 10 messages, and until somebody comes in and processes one of those messages, we're not going to be able to add any more messages to the collection. So this is actually quite possible, and it's done by a wrapper around the actual collections that we've just seen, and the wrapper is called a blocking collection. So the idea of a blocking collection is something which can, if you wanted to, it can actually block on the elements that you are consuming and not let you add any more elements, for example. So let's take a look at how that works. So I'll make a blocking collection of ints. So we're going to keep integers. Let's call it messages equals new blocking collection of int. Now, if you look at the arguments of blocking collection, you can see that there are 2 things here. First of all, you can specify the underlying collection that you want to use for the blocking functionality. So in this case, you can use a concurrent bag, a concurrent queue, virtually anything which implements iProducer-Consumer Collection. So here, for example, I can make a concurrent bag. Let's say I don't care about the order in which messages come in, just give them to me as they come in. So that's a concurrent bag. And let's take a look at the second argument. The second argument is called bounded capacity. So essentially this defines how many elements we can have at most. And what will happen, surprisingly enough, let's suppose we put a 10 here. Let's suppose there are already 10 messages in this blocking collection. What would happen as you add the 11th element is the collection would block. That's why it's called blocking. It would block and it will basically stall whoever is trying to add the element until such time that a slot becomes available to add the actual message. So let's take a look at how we can use this and set up the full producer and consumer pattern. So what I'm going to do here is, first of all, I'll make a cancellation source because we might want to cancel the whole thing at some point. So I'll make a cancellation token source, CTS. I'll make it here so that it's available to all parts of the code. And then I'll have the producer and the consumer. So I'll have the producer as task.factory.startNew. So this is going to be run producer. Okay, let's actually make this function. So here's the run producer method, and we'll do a similar thing for the consumer. So consumer, and this is going to be called run consumer. So we have separate tasks, effectively separate threads, which take care of the production and consumption of integer messages in this case. So I'm going to make the producer first of all. So what the producer is going to do is it's going to do an infinite loop. Let's go into the producer. So we're going to have an infinite loop here while true. What I'm going to do is first of all check whether cancellation was requested, because if it was, I just want to break the whole thing. And then of course I'll generate some random value. Let's have a random number generator. So I'll make one up here. So let's make random equals new random, like so. It also has to be static. We're doing everything in a static fashion. So this is going to be random dot next, say to 100. And then what I'm going to do is add it to the messages. So I say messages.add. I'm going to add this value. Then I'm going to right line the fact that I did in fact add it. So actually what I'm going to do is put a plus in front of it. So I'll right line the fact that I've added this integer I. And let's put a tab at the end of it so that we can see it later on. And then I'm going to sleep. And just for the fun of it, I'll make the sleep time also random. So I'll do random.next. And now put 1 second in here. Okay, so that's my producer. Now my consumer wants to somehow go into the blocking collection, but it only wants to do it when there is an element there to process, because there is no point looking into it if there is something, if the collection is empty, for example. So how do we do it? Well, luckily enough, the blocking collection gives us an additional enumerator for it. So what you can do is you can say for each var item in messages dot get consuming enumerable. So this is a special function which is going to basically, as soon as somebody adds the element, it's going to give you that element and you can proceed in your iteration effectively. So that's very useful because it means that you can have this task, we're going to have it as a task, and you can basically have it just block whenever there is no element to process. It's just going to wait for the next element to come in. Simple as that. So essentially here what we do, we of course check for cancellation, and then afterwards we get the item. Notice we're getting the item by virtue of doing a for each, so we don't have to manually remove it from the collection because we just got it from the for each. And this consuming part means that we've consumed it, we took it out of the collection, and we basically got a copy of it stored in item. So that's where we're going to use it. So I'll right line the fact that we sort of removed it from the overall thing. I'll put a minus in front of it, and then we're also going to sleep for a random number of seconds. So I'll do random.next once again, up to a second here. Okay, so we have the producer, we have the consumer. All we have to do now is fire the whole thing up, and I'm going to actually wait on both of these tasks in a separate thread as well. So let's call this one produce and consume. So I'm going to basically do a task wait all. So let's do a try. I'll do a task dot wait all for the producer and the consumer. I'll stick the token in here, even though the token will automatically just cancel all of them. I'll just put it in here anyway. And then in terms of the exceptions, well, if it's canceled, we get an aggregate exception, as you've seen before, and then we can just handle it for all the types. So I can say ae.handle and just get the exception and return true, whatever the case happened to be. So we are expecting exceptions due to cancellation. Okay, so that's our setup. We need the main function, obviously. So static void main and all the rest of it. And in here, what I'm going to do is I'm going to use task.factory.startNew, and I'll run this produce and consume operation with the token provided here, and I'll read key, and whenever I press the key, I'm going to cancel on the token. Okay, so just to recap what's going on here, we have one thread which is producing items, producing integers, posting them inside the blocking collection, and then sleeping, and the other thread is using this get consuming enumerable wrapper so that we get the item as soon as it's posted and we process it. So let's run the whole thing and see how it goes. Okay, so you can see that we're sort of adding 81 and processing 81. Let me actually press return here so that we can pause. You'll see that at some points we're adding 3 items and we are removing 2 items. So we can try to manipulate the addition of the items so that we get some sort of overflow. So we add too many elements effectively. And for that, what I can do in the producer, I can just remove 1 0 here. So now we're producing elements 10 times as fast, which means if I execute this, you'll see that we have very few minuses, but lots of plus. We have something like 10 pluses in a row. So curiously enough, we will never get more than 10. You can see that there are 10 items here. We'll never get more than 10. And the reason for this is that the blocking collection is bounded. We specify that the number of elements that can accumulate there at most is 10. So what happens is when you actually go and you add the element, when you actually call messages.add, if there is already 10 elements here, this thread is going to block. And that's why it's called a blocking collection, because at this point, you basically just get stuck until somebody allows you to add those elements in there. So just to recap, blocking collection is not itself a collection. It's just a wrapper around some underlying collection which implements this curious iProducer consumer interface. What you do is you make one whenever you want to set up this producer consumer pattern, and then what you do is you use get consuming enumerable if you want to consume the items, and you add the items in the typical fashion. So that's what